All right. Sorry we're a little slow. Emily and I were both having some technical difficulties up here. So who'd like to start us off? Sure. Thanks. Thank you. Right. Just a heads up, I will not be here Thursday or Friday. So Chelsea will be here teaching Friday, but I won't have office hours either of those days, and I still don't have office hours on Tuesdays. Hopefully starting in November, I can have office hours on Tuesdays again. So I have a conference, it's just in Salt Lake, but I'm going to have to present about the same time as this class is building, so I can't do both, sadly. So while you're working on this, let me just say a few things. We are getting back into some applications, and I mentioned before that the purpose of these applications is not because they're the most important applications. They're just trying to give you a variety of contexts to help you get comfortable understanding what an accumulation problem looks like, what an integration problem looks like, and the thinking and reasoning behind how to chop up a situation that you can't handle holistically, chop it up into small pieces, handle what's in each piece, and then put that together in a sum and an integral. So you could get through this class, and you might know how to do areas between curves and volumes and work and arc length and hydrostatic force and surface area of revolution and centroids, and wait, I know the applications. But if you can't take a new situation, recognize it as an accumulation or integration type problem, and have the skills to reason through and chop it up, and figure out what integral it would you have to use to get that the calculation you're after, then we have largely failed as a class, because this class is not just about these applications. These applications they're trying to set you up so that you can understand the reasoning behind these problems, so that you can apply it to other situations. So that's one reason why we try to emphasize the reasoning behind each of these. If the arc length formula was really all you needed to know, then hey, yeah, we could just give it to you. But there's something about understanding how to get that arc length formula that's important, because it can help you in this situation. There's my pen. Okay, so please be honest in your iClicker quiz. Okay. So I'm going to start going through this. So I'm going to write the arc length formula up here, and then after we do this problem, we'll reason through it. So. Yo, you're just setting up. Yep. Yeah, set up right there. Yeah, this might be one of those impossible problems, so that's why just set it up. Yep. Get it to the point where you start crying. Oops. Just kidding. Yeah, so right there is just fine. Okay, so chime in. If you got it right. If you didn't get it right. So, any questions right now? Yes? When you did what, sorry? Right here, this 2x? Okay, so the question is, why is this 2x in the numerator? So when we take the derivative of the natural log of something, the derivative is 1 over that something, but then with the chain rule, you multiply by the derivative of that something. So you always end up multiplying with the chain rule. So it's multiplied by 2. Thanks for asking that. Oh, right. Yeah. U sub is what we do to undo the chain rule, so it makes sense to do U sub here. In the denominator. Okay, other questions about this particular problem? Okay, let's talk about the arc length formula. So I'm going to talk about this in 2 different ways. So one, we can use the distance formula. And the idea here, let's take a step back first. If you've got a curve like this, we don't have a nice way to calculate the length over that whole curve. What can we do? Where have you seen calculations of length before? Distance formula. We can calculate the distance between 2 points. So one strategy might be, instead of trying to calculate that, to calculate this curve, is to chop it up into lots of small lines. So then you can find the length of each of those individual line segments, and we can find the length of an individual line segment no matter what angle it's on. So let's zoom in a little bit here. So to emphasize, we've got a point here and a point here, and this we can call x1, y1. This x2, y2. And so the length of that dotted line there, that will be the square root of x1 minus x2 squared minus y1 minus y2 quantity squared. Not minus, plus. Okay, so using the distance formula, using the Pythagorean theorem, same thing, we get that. Now, we can think, especially if we're thinking about this as just one small section where we have a delta x, we can just think about this as delta x, which is the difference there. And we can think about this as delta y. So we could rewrite that as delta x quantity squared plus delta y quantity squared. And then we do the natural thing, which is we're going to factor out a delta x. That was a joke. Okay, that's not the natural thing. So, but we are going to factor out delta x squared. I don't like this way of deriving it. I like the other way of deriving it, but we'll get to there. So 1 plus, this is what the book does, by the way. Delta x squared. Okay, and we can pull out the delta x. We get that times 1 plus delta y, delta x quantity squared. And now as you take the limit, well, actually we need to add up all of those. Add up those n pieces. We can do that for each of the pieces along here. And then if we take the limit as n goes to 0, I mean infinity, n goes to infinity, or the limit as delta x goes to 0, what happens over here, particularly with this piece? What happens to delta y over delta x as delta x goes to 0? Becomes dy dx, the change of y with respect to x, which is the derivative. So we get the derivative squared 1 plus that dx going from x equals a to x equals b. Okay, so there's one way to derive it. For me, this way, it's still not clear why the derivative should be in there. So let's approach it another way. But I actually should stop. Questions so far about what we've done? This way seems a little bit more like magic to me. So I hope this one doesn't seem quite so much like magic. So we're going to start off with the same situation. Let's call this delta x. And I'm going to draw a tangent line. So this is tangent to the curve right here. So where this tangent line hits, so that much is delta y, but that's pretty close to this much. And especially as we take the limit, if we have a differentiable function, those 2 points will get arbitrarily close to each other. But this distance is also f prime of x times delta x. So think about what you know about what derivatives mean. Think about what you know about what slope means. And explain to your neighbor, or I should write xi. So this is the derivative. We'll call this point xi. So I'm looking at the derivative there. Why would the distance from this point to this point, why would that distance be represented by the derivative of the slope here times delta x? So think about it for a second, then talk to your neighbor. All right. Who heard a nice explanation we could get to it? Who gave a nice explanation? If you said it, then you heard it. Are you pointing to your neighbor? All right. What you got to tell us? Get something.
Well, I was like, the curve looks like to the second degree, so I know the derivative of that would be like a linear line. And so I was like, that would be the derivative of it, so you have to like change the next, because that's how far you can go.
What's your name? Let's hear from Megan, everybody.
The derivative is the slope, which is the rise over the run, which is changing y over changing x. And so changing x cancels, and it's still changing.
That was Christian. Let's hear it for Christian. Someone else have an explanation?
So since you're taking the derivative of a certain point xi, it doesn't matter what polynomial or fluid it is, or f
Nicolo. That was Nicolo. So Nicolo is kind of generalizing, is it Megan's thing, like you actually, it doesn't actually have to just be a parabolic curve. Any curve we could get, we could find this tangent line and get that slope. So you can think of the change in dy dx as a change in y over the change in x, right? You can think of the slope as that, and if we multiply that, those divide out, we get the delta y. So that's the way that Christian was thinking about it. But the meaning of the slope actually is, it is the factor that you multiply a little x by to get this height. So it is the ratio, it is the kind of multiplier that you multiply the dx by to get your dy. So that's another way to think about slope. It is the rate of change. If you move a little in the x direction, you multiply by the slope, and that tells you how much you change in the y direction. So if you think about slope that way, then it also makes sense. So hopefully some way we've agreed that this makes sense. And now we can start to do the same thing where we have delta x squared. We can use the Pythagorean theorem. Delta x squared plus f prime of x delta x all squared. And we can pull out our delta x now. And you get 1 plus f prime of x quantity squared. And that looks a lot more familiar to us. That should be xi. And then we can add those up. And we end up with the same thing as we take the limit x equals a to x equals b of the square root of 1 plus f prime of x quantity squared dx. And thinking about the slope as a multiplier actually helps us out to make sense of this. Dx is a little piece of, it's a little movement this way. Let me draw it again down here. So here I've got a dx, or a delta x. And f prime of x will tell us this height. But what we just derived right here will give us, it's what we multiply dx by to get this length. It is how much this dx stretches to go from here over to there. Depends on the slope. Right, you would expect a higher slope. A larger slope should give us a larger arc length over that period, right? Over the value from here to here. Okay, here, let me take a step back. What is the shortest distance I can get if I go from here over a dx to here? Straight line, and that length is going to be dx, right? So if I have a multiplier by dx that's going to give me the arc length, what is the smallest that multiplier should be able to get? 1. It better be able to get 1. And what do we have to get that multiplier 1? What does this have to be? 0. And when is the derivative 0? Over a period. It's when it's a horizontal constant. So it makes sense then that we have a multiplier that at minimum would be 1, and when it is 1, it should be just a constant to go from this length to that length. What happens if I shift a function up and down? Should that change the arc length? No, it shouldn't change the arc length. How does that play out in our arc length formula right here? Talk to your neighbor. Tell your neighbor. All right. Not as much talking as I would have liked, but someone tell me, how does that play out here? How does shifting up and down? How do I know that shouldn't change the arc length?
Well, when you shift up and down, you either add or subtract a constant, and then when you take the derivative, the constant goes to 0, and thus it has an effect.
That's right. So anything that I added or subtracted to f of x, it won't come into play in this formula because I'm only dealing with the derivative. So, okay. Let's do a more interesting problem. Okay, maybe this isn't a more interesting problem. But. Okay, when you guys work on that, there is the function going from x equals 1 to x equals 2. Can you start to calculate what, can you actually calculate what the arc length is? Okay, so I saw a lot of people get to this point. Okay, and what do you do once you get to here? What's an option? What's a strategy? Okay, you can expand it out. Okay, so multiply the x squared, the x halves minus 1 over 2x by itself, and you get x squared over 4 minus, you end up with 1/2, because you get the x times the, divided by the x will get you just a 1, and you get a 1/4, but you get 2 of those, so 1/2 plus 1 over 4x squared, and you get the 1. Now, where do we go from here? There's a couple different options. One of them works out nice. I don't know how the other one works out. But there's probably multiple things you could do from here. Okay? So let's just throw out some options. Okay, combine our like terms. Add in the 1 there. Okay, what else? Okay, get a common denominator. Okay, and combine. What else? You might start thinking trig sub. That might come up. Someone said factor. let me combine them with the 1 and so this is the factoring technique. Right, that's what you're saying is you can rewrite this as x over 2 plus 1 over 2x. Is that what we had before? Quantity squared, right? Yeah, so this is the factoring strategy that you can take that thing and rewrite it, and it's really close to what we had before. It's really close to our derivative that we had squared, except we had a negative sign, now it's positive. Okay. Because the formula involves a sum underneath the square root, the arc-length formula does, and also next section where we do surface area of revolution, it also does. It's really hard to actually find a function you can take the derivative of that we can actually do by hand. So the book has to be really, really tricky and try to find things that you can actually do. And one strategy it uses is it will find things so that when you multiply it out, you end up with that negative 1/2. And you add the 1 and it becomes a positive 1/2. And then you can factor it down to what you had before with the derivative, except it becomes positive. So like probably half the problems in the homework section, not necessarily that we've assigned you, but probably half do this exact same trick. So don't get, you should look for that, okay? It's not the most important mathematical thing to know here, but it can save you lots of work when you're trying to work these out that you might lose when you do one of the other strategies, okay? But if you end up with that 1/2 and that negative 1/2, add the 1, get the 1/2, see if you can factor it back down to a perfect square. Okay? Once we do that, then it's just 112 from there. So you get x over 2 plus 1 over 2x and you get x squared over 4 plus the natural log of x over 2. You're going x equals 1 to x equals 2. And we're going to stop right there. So on this problem. Okay? So things can get kind of crazy with some of these. You can see that you're probably going to end up with some trig subs just with the nature of the nature of the formula. You're going to have 1 plus something squared. You can imagine that the square root of 1 plus something squared, you can imagine some trig subs coming up with that, couldn't you? So, okay, any questions with this problem? Okay. All right. Okay, here I've got here I have a marker. Okay. I think it's about 4 feet. About 4 feet. Maybe 4 feet to there. Okay. I'm gonna try to toss this. So it goes up 4 feet, but also over 4 feet. So maybe from there, oops. To there, to there. Okay? Let's see how well I do. Not super exciting stuff. Okay. This is the marker toss of death. Dun dun dun. Hey, that was pretty close. Thank you. Okay, my question for you is, how far did that marker travel from this x to that x? Go. Okay, well, before I turn it loose, what do I mean by how far? That's kind of an ambiguous question here. So one answer to that would be what? How far did it travel? 4 feet. Yeah, went over 4 feet. This way. What's another answer to that question? So it's 4 or 8 feet. You might say went up and down 4 feet. Okay. Before we calculate it, let's get some bounds. What's a nice upper bound here? Give me a number that you know cannot be, that has to be higher than the actual length of this path that I heard. Someone raise your hand. 4? Oh, so 4 you know is a lower bound, right? Okay. How about an upper bound? 12? Why 12? Okay. So how about a lower bound? We can get a little bit better than 4. So 8. So there's 12 right there. 8. We know it went up and down, so we know it had to go at least 8. So somewhere between 8 and 12. Okay. Let's do a quick iClicker quiz. So if you're just gonna, if we find the right number and round, you're just gonna get the whole number of feet that's closest. So we're gonna calculate it. Okay, so we're gonna calculate it and then round. Is it closest to 8 feet, 9 feet, 10 feet, 11 feet, or 12 feet? So just click in and click A, B, C, D, E. And yeah, we're actually trying to find this path that it's supposed to go up, over, and down. And you guys know all of the pieces to this problem, but let me just get you started off a little bit. It makes it a little bit easier if we put the y-axis right here, and we can call this a negative 2 feet, and we can call this 2 feet. And so this is the point 0, 4. Okay? So right now we've got about half of you are at C. The next choice is B at 27%, and then B at 20%, and then just very few at A or E. Okay. All right. Okay. See what you can do to figure out that length. You got some points there. You'll have to figure out exactly what that function is, and then go from there. All right. So I saw a lot of you get to hear, and then you were a little bit hesitant. First, any questions up to this point? So actually, to find the function first, there's a few different strategies. One, you know that the constant, if we set it up this way, has to be 4. So you can think of it as x squared plus 4 with some constant. You've got to figure out what that constant is in front of a instead of in front of x squared. You can use one of your points. I used the point 2, 0. And then I plugged in 2 and 0 to figure out that my a equals a -1. So, I mean, we'd know from the shape of the graph that it's going down that it should be negative, but we don't know if it was a -0.5 or a -2 or a negative something else. So then I took the derivative and plugged it in, and I get this. So what should you be thinking here? Trig sub. So, yep, that's why we worked on trig subs. We learned in a lab a few weeks ago that the back tire of a bike knows trig subs. Now you know that flying markers also know trig subs. So 2x equals, we want 2x to equal tangent of theta. So x equals 2 tangent of theta. And dx equals 2 secant squared theta d theta. I'm not going to carry my bounds through, so I get the square root of 1 plus tangent squared theta times secant squared theta d theta. Oh, over 2, yep. No wonder I heard so much talking over there. So, get the 1/2 out there. Okay, so 1 plus tangent squared is secant squared theta. So what do you end up with? You end up with secant cubed. It just comes up. It's kind of crazy. Who knew that doing something you've done many a times, tossing something in the air, there was the integral of secant cubed there if you just asked the question. How long is the path that it takes? Yes? Oh yeah, there's two 1/2s here, right? Oh wait, there 2 1/2s? No. So I kind of split this. I mean, I kind of skipped this step. You did have 4 tangent squared thetas over 4, right? When I put this piece in here and squared it, so I had a 4 to cancel that with the 4. So, okay. And you can do just 0 to 2 and then double it because it is symmetric. Okay, we're not going to go through secant cubed. I did suggest you memorize it because it just comes up. It's the average of the derivative and the antiderivative of secant. So I know you guys don't do this class enough to remember that, but when you teach it all the time, you can. So secant of theta, tangent of theta, plus the natural log secant of theta, plus tangent of theta. And then you either need to get your bounds back in terms of theta, or in terms of theta, or put everything back in terms of x. And has anyone done this all the way through? Punch it out in their calculator. What did you get? 9.29. So if you picked it was closest to 9 feet, then you got that right. So pat yourself on the back. All right. Really fast. I'm going to show you an arc length problem I did. This is a map of I-15 going around Point of the Mountain. So from Utah County here up to Salt Lake County there. You'll notice it takes the jog to go around the mountain. It does go up a little bit. So I was wondering why they didn't go through the mountain. Most of the mountain is sand anyway. Back when there was Lake Bonneville with the currents, it would just deposit a whole bunch of sand right here. That's why I pointed mountain is that plant operation going is they just have a big pile of sand that they use. So it does get to be rock in here somewhere, but all of this I know. So why didn't they just go through the mountain? Because I wanted to know how much we're wasting in gas going around point of the mountain. So I put a few points on here. So put C, D, E, F, G, I, H. I put that on there. I fit a polynomial, and that's f of x right there. So that's my polynomial that goes through all those. It's a pretty good fit. But now I need the arc length. So the arc length, so that's the integral of the square root. I'm typing this in at the bottom. I don't know if you can see it very well. The square root of 1 plus f prime of x. I do have it already. I already took the derivative of it. Oops. I think I hit caps. But in GeoGebra, you can just write f prime of x and it'll do the calculation for you anyway. So the square root of that, I have to square. Square the derivative. Yep, so there, is that better? Yep, and one there. I just need, okay, then we're going to integrate with respect to x, and we're going to go from, yeah, I'll get, that's for my integral command, so we'll get that. But I'm going to go from x, the x coordinate of c right here, to the x coordinate of h. So the x coordinate of c is 0.58, and the x coordinate of h is 7.78. And if I did this right, that's not right. I don't know. I already have it right here, so that's why you're prepared. So here's the integral of the 1 plus the derivative square rooted from 1.5, or sorry, from 0.58 to 7.78. How many miles do we get? 8.52 miles. But what if they went straight? So distance from C to H, 7.2. So about 1.32, about 1 1/3 miles longer. Okay, so how much gas? So if you assume there's 2 cars per second going past point of the mountain for 18 hours a day, right, for 365 days a year, gas right now it's like $2.7. Yeah, about $2.70 a gallon, and each car averaged 25 miles a gallon, which is probably high. Average 25 miles a gallon. You know what we get? This number right there, over $4 million. So we spend over $4 million a year just in gas to go around point of the mountain. And now, what was that? That's just, it's just total. So per person, if it's divided by how many people we got. And so we're also pumping out $4 million worth of gas unneededly into the atmosphere. They should have gone through it. All right.